In this work, we propose a pose-guided Gaussian splatting framework for human novel view synthesis. Our method is specifically designed to tackle challenges such as fast motion and self-occlusion. Traditional Gaussian-based human modeling starts with multi-view images. A network first extracts features, followed by depth estimation, which then produces Gaussian parameters for 3D splatting. Our pipeline introduces a dedicated pose stream, where color images are fed into a pose estimator to extract human poses. Our framework remains agnostic to the choice of pose method or representation. For instance, either 3D joints or 2D heat maps can be used to serve this purpose. The pose features are then fused with color features to provide richer input to the depth estimator. To illustrate the role of pose guidance, consider the analogy to character rigging, where Gaussian primitives are loosely anchored around joint locations. This structural supervision helps the model better estimate depth and motion, and reduces the risk of detached Gaussians drifting away from the body during fast movement or occlusion. Temporal coherence. Beyond feeding pose features into the depth estimator, an auxiliary pose pathway inputs these features into the TPS module, which employs a gated recurrent unit network. This module refines pose estimates by leveraging temporal cues. For example, joint positions from the previous frame constrain and guide the estimation in the current frame, improving stability and reducing jitter during fast motion. Encoders and decoder. The original CNN block is replaced with 3 modality-specific encoders for image, pose, and depth map inputs. Each encoder extracts features from its respective modality. These intermediate features are fused and passed as skip connections to a multimodal Gaussian decoder, similar to the residual pathways in a U-net architecture. The decoder then produces the final Gaussian parameters for 3D rendering. To visually demonstrate robustness beyond public benchmarks, we captured sequences featuring a diverse range of motions and occlusions. In this scenario, where the arm motion is relatively slow, our method delivers favorable results compared to other approaches. The zoomed-in view reveals fewer scattered artifacts around the arm, with a more clearly defined boundary. As we rotate the virtual view to the back side of the person, an area typically self-occluded and outside the camera views, our results show a more complete and compact reconstruction, with fewer scattered or floating Gaussians. This is due to the pose constraints, which help maintain alignment of body parts and prevent them from drifting. Here is another scenario demonstrating self-occlusion. As the subject opens and closes arms, the inner arm becomes occluded during the moment of crossing. Our reconstructed 3D representation preserves a clear separation between the two arms, even in regions not visible to the input cameras. While our approach performs well for less rapid motion sequences, noticeable artifacts may still appear during high-speed movement. However, it significantly reduces detached primitives compared to other methods. We also assess temporal coherence across frames, especially under motion. Full comparisons with state-of-the-art methods are provided in the supplementary materials. Our approach maintains consistent quality throughout.